Hi ladies and gentlemen, welcome to lesson 6. Today we're going to talk about solving linear systems of equations. We're going to do this and mesh it with the stuff that Strang is talking about. His conversation is really limited to elementary matrices because what he's trying to do is provide us with a matrix way of thinking about linear algebra and these concepts. And where he's heading is what's called the LU decomposition. And we're going to get there in a couple of lessons. However, there is the foundation for this, which is really based upon Gaussian elimination and row operations. And because we have operations researchers and data science majors as the primary recipients for Math 344, we're going to dive in and spend some extra time on these important topics. So let's jump in. This is going to be a slightly different resource we have here. I have an excerpt from my textbook on linear algebra, and this is section 2.3, which is Gaussian elimination. As always, it's not shown here in a size where you can really read it. However, a PDF is provided so you can follow along with the conversation. It starts straightforward enough, and you'll see that there's a lot of overlap between what I'm talking about and what Strang is talking about, because ultimately we're still talking about systems of linear equations. So systems of equations we generally write as ax equals b. That's fairly consistent. And what's important, and a skill that you have to have, it's not difficult, but a little bit of practice and you'll be with it. So we have a system of equations with m equations and n unknowns. And we are going to write this in matrix vector form, which is what gives us the ax equals b. That's a pretty easy transition. You have to be able to go back and forth between these two representations. The next thing that's discussed here is backward substitution. We've already looked at that. This is a simple example to say, hey, if we already had a system in triangular form, we'd be set because all we'd have to do is back substitution, which is fast and easy. And what I want to do is provide you a little expansion of this example right here, which I've copied over, just to take a look at some of these transitions and some of these fundamental ideas. So first things first, what we're going to do is we're going to take a look at how does this appear when we put it in matrix vector form. So in matrix vector form, we have the coefficient matrix, which is going to be 1, 2, 3, 0, 0, 1, multiplied times the vector of unknowns, which is x1, x2, x3, and then we have the right-hand side vector, and the right-hand side vector in this case is 10, 3. And what we can see that this is obviously the ax equals b format that we're talking about for matrix vector form. And what I want to highlight is just a little bit of what this means. Remember, we talked about this, but it's important to keep in mind the rows are always equations. As we go through the process of Gaussian elimination, whether we're doing it with row operations like we're going to talk about today, or the elimination matrices that Strang talks about, the rows are always equations. We can stop at any point and write those equations down. Let's just think for a minute, and this is outlined here in the text. I just want to talk a little bit more about it to provide you with the vector representation to the solution. We can very easily see where we're headed here. So obviously we already know that x3 is equal to 3. And when we substitute that into the top equation, we have x1 plus 2x2 plus 9 equals 10. And solving for x1, we end up with 1 minus 2x2. So we have the representation for x1. So we know x1 and we know x3, given that we have x2. And that's really the key to think about here. x2 is what we call a free variable. It's free for us to choose. And this is really the hallmark of operations research. We oftentimes have objective functions which we're trying to optimize, and we have constraints that we are bound to. The equations in this case are the constraints, and you'll hear me use those terms interchangeably. The equations, constraints, same thing. And what we're trying to do then is look to see what is our solution space where we can go in and choose our solution. In this case, we have a free variable, and that means we have something that we get to choose. So if we had an objective function, we would choose the x2 value to optimize that objective function. And that's at the heart of operations research. In this case, we're just going to leave it as a free variable, and we're going to write down our solution as a vector. So if we say that x vector is x1, x2, x3, which is what we wrote when we had this over here, then what we have is the following. We have x1 is equal to 1 minus 2x2. x2, of course, is just x2. It's whatever it is. And because of that, we have an equation in here, x2 equals x2, which seems a little ridiculous, but it allows us to keep track of the accounting for what our free variables are. And then finally, we know x3 has to be 3. So we can rewrite this, and this is equal to a constant vector, which is 1, 0, 3, added to x2 multiplied times another vector, which is negative 2, 1, 0. And this is the vector representation for our solution. We have a part, a direction, if you will, that is associated with the free variable. So if we're optimizing along this vector negative 2, 1, 0. And then the constant piece is 1, 0, 3. That is a particular solution, similar to particular solutions that you may have learned about in other topics like differential equations. I just want to show you this. It's not in the textbook, so I just wanted to show you that this is kind of our ultimate goal for writing down solutions for the systems, because it allows us to gather a lot of information about what our free variables are, what our variables are that are not free. So you'll notice that x1 and x3 are not free variables. We have a term for those. x1 and x3 are, in my textbook, they're called fixed variables. And in Strang's textbook, he calls them pivot variables. They mean the same thing, fixed variables, pivot variables. There are other names for them. These are the variables that once we select values for the free variables, these things are determined. So fixed, pivot, whatever. And the reason that he calls them pivot variables will become clear once we talk about the reduced row echelon form. So before I leave this, let me just highlight for you, right here is the term free variable. And the next thing we have is a definition for consistent versus inconsistent, right? So, sorry, I said those backwards, but we have inconsistent and consistent equations. Those definitions match exactly with the definitions that Strang has in his book. You can read through here. There are some examples down here that give ideas of what consistent and inconsistent systems are. Here is a system of equations which we convert to be an augmented matrix. We talked about this before. We always want to deal with an augmented matrix whenever we're doing row operations or elimination matrices, because that keeps us from having to track the left-hand side coefficient matrix versus the right-hand side vector. So we just pile these together into one matrix called the augmented matrix, and the augmented matrix is something that we operate on all the time. All right, so a key to what is at the foundation of solving these systems are elementary row operations. So I've mentioned this before. Strang really doesn't talk much about this. His book is not so much oriented for operations research folks. It's more geared towards an introduction to the mathematical side without proofs for linear algebra. So the row operations are exactly the things we can do whenever we're solving system of equations. And they're listed there. I won't read them out for you. You can read them for yourself. But what I want to do is make sure that you understand that Gaussian elimination is the process of applying the elementary row operations. This is really what we're doing when we apply the elementary row operations, or row operations, is we are executing Gaussian elimination. This is obviously not a new idea. Gauss lived in the 1700s, and this was an idea he came up with at that time. Of course, with computers, it's become much easier to execute this, and we're going to do some examples. Let's see. So we can go through this, and we'll do an example in just a minute, but you can look through the process. There's an explanation here. What I want to highlight for you is a difference between what's in my book and what's in Strang's book. And it's not that either one is correct or incorrect, it's just a difference of emphasis. So in my book, I'm always converting the pivots to being what we call leading ones. So the pivots are leading ones. Strang in his book is leaving the pivots as non-unitary values if that's what they are. If there's a 5 in the pivot, he leaves it as a 5 in the pivot. And he's doing that on purpose. So where Strang is headed, as I said earlier, Strang is heading everything towards the LU decomposition of the matrix A. And we'll talk about that. But that's not my point, and that, in fact, that decomposition is nowhere to be found in my textbook. So what I want to do is just show you the process that we go through to actually execute the steps for Gaussian elimination. They're provided here. I highly recommend that you just load up this matrix in MATLAB and walk through. Once you've gone through a few of these, you'll begin to see the patterns and see how straightforward it is to do these calculations. The result of having done Gaussian elimination is something that looks like this, which is in what we call row echelon form. So let me write that down. This is in row echelon form. And we'll talk a little bit more about that because the next section in the book, section 2.4, is exactly row echelon form, and I'll discuss it a little bit more there, although it's not really a big topic for us in this course. So once we have things in row echelon form, you can see that the idea of back substitution is going to be straightforward. And that's the discussion that happens here, is this idea that, hey, we could just do back substitution and solve the system. And Strang talks about this at length because back substitution is an order n squared operations. So we don't do a lot with operation counts, but there are a couple of things every once in a while that we'll mention that you need to keep in mind. One of them is matrix multiplication. So matrix multiplication, which we talked about in section 1.4, that is order n cubed. That is an n cubed operation. In other words, if I have two n by n matrices and I take their product, it's going to take n cubed, about n cubed operations for us to be able to do that multiplication. That is extremely expensive. We do not do matrix multiplication unless we absolutely have to, because n cubed is outrageously expensive. In modern computing, our goal is to try to reach things down on the level of order n times natural log of n. Okay. And that's called n log n. N log n is pretty fast. Okay, order n is, of course, about as fast as we can go, but we rarely find algorithms that are that fast. And in between these two things is order n squared. So order n squared is much faster. Just think of a matrix that's 1,000 by 1,000. If I have 1,000 by 1,000 matrix and I have to do n cubed operations, right, that's 1 billion operations. Order n squared is 1 million operations. It's 1,000 times faster. That's what the difference we're talking about here between n cubed and n squared. And then order n log n is considerably faster than that. So the back substitution, and Strang talks about this, is order n squared. It's a fast thing to do compared to matrix multiplication. So if we were given a system like this, we could solve it pretty quickly. Of course, that doesn't happen. We have to go through the steps of Gaussian elimination to create something like this. So that begs the question, should we do back substitution, or is there something else we could do? And that's Gauss-Jordan elimination. Gauss-Jordan elimination is outlined right over here, and it starts here and comes down, and that's the process of, in essence, doing the back substitution, but doing it systematically. What we end up with when we do Gauss-Jordan elimination is a matrix that looks like this. You'll notice that above the pivots, all of these values are also 0. So we've not only eliminated down, but we've eliminated back up again. And the beauty of that is the solution is now trivial. Remember, every row is an equation. So the bottom equation just tells me x5 equals 1, and the next equation tells me x4 equals 4, and x3 equals 3, and x2 equals 2, and x1 equals 5. I can just, there's nothing to getting the solution. It's right in front of me. So that's our goal, and we'll talk more about that when we talk about reduced row echelon form. So the other topic that I want to provide for you is just a brief discussion about the row echelon form. So row echelon form, there's a description here. That's not part of this course. If you want to read through it, that's fine. It's worth noting kind of the general structure. It's what you would think we would get after doing Gaussian elimination. You can see that we have pivots, which, like I said, the traditional way of creating the pivots is to make them a value of 1, unless you're doing LU decomposition like Strang is doing, and then you're not going to make them 1. But you can see the pivots are here. When we're in row echelon form, we are prepared for back substitution. We're all ready for back substitution. So there are some examples of things that are in row echelon form and things that are not. This is an important result, but we're not really covering it in this class. We'll get to an equivalent important result when we get to the reduced row echelon form. And same thing here, right? Every matrix is row equivalent to a matrix in row echelon form. And what that means is, no matter what matrix we are given, we can always apply Gaussian elimination to it, and we can always put it in row echelon form. And we'll see that that's also true for reduced row echelon form, which is a topic we'll talk about in a couple of weeks. All I wanted to do is, if you're looking for a little bit of a different approach, a different way to look at the elementary matrices that Strang is talking about, so he talks about the elementary matrices, and I have the same conversation. Of course, we're covering the same topics here, so there's nothing new or different. So the elementary matrices, my representations are different. I use R for my elementary matrices, and these are the 3 standard elementary matrices. I put a little bit more kind of a descriptor in the way I write them down as compared to what Strang does. And they're really representative of the 3 row operations, which are swapping rows, that's the first one, multiplying a row by a constant, or multiplying a row by a constant and adding it to another row. Those are the 3 things that are our elementary row operations. And I just depict them differently. Not part of the course, it's just here if you want to take a look at it. There are some examples here. There's one thing that I will tell you, which is my representation, just again, so that when we're reading through the next section, you're able to follow along with what I have for notation. You'll see that what I have is R with a big scoop on it, multiplied by some matrix. B is giving us U. So my U means the same as Strang's. It's upper triangular. It's some matrix that is upper triangular. My R matrix with the big scoop is just the product of all the elementary matrices. And this is what Strang calls capital E. It's the product of all of his elementary matrices. And that's really it. We're going to work some problems in class. And other than that, what I want you to do is practice with the Gaussian elimination. To that effect, let's go through an example. And what I'm going to do is pull up my matrix B, and I'm just going to show you how we would do this, just to give you an idea so that when you're doing this and when you're walking through the example that's in the text, you can follow along. So we're going to, first things first, I'm going to change this 2 to a leading 1. I'm going to make this a 1. Remember, Strang doesn't do this, but we're going to do it. So we're going to take the first row, that's the representation for first row, and we're going to set it equal to the first row, but we're going to divide by the value that's at 1, 1. So we're going to replace this first row here with the first row divided by 2. And when we do that, we end up with this representation right here for the matrix. And you can see MATLAB's standard format, which is the short format, which has the decimal places associated with it. Now, what's the next thing we do in Gaussian elimination? We're going to use this leading 1 here to eliminate the 1 and the -2 and the 2. So let me just show you how this goes. So B, second row, the second row is going to be equal to what? It's going to be equal to the second row minus 1 copy of the first row. So it's going to be the second row, that's second row, all the columns, minus 1 copy, and I'm just putting the 1 in there to be a little pedantic about it, B1 comma colon. So this says replace the second row with the current second row, which the current second row that we have minus 1 copy of the first row. And when we do that, you can see that we have obtained our goal, which is to have this 0 down here. Now let me lift this up a little bit so that it's a little bit easier for you to see. All right, it's giving me some trouble on the orientation. There we go. All right, there you go. That'll be a little bit easier to see. So now the next thing we want to do is we want to eliminate the negative 2. So in MATLAB, remember, like many programming languages, we can just hit the up arrow. And the up arrow will cycle back through the previous commands that we've used. Well, one up arrow gives us the command that we had, and what we're going to do now is replace the third row. So the third row is going to be equal to the current third row, and then what do we need? We need to eliminate the negative 2, so we need to multiply the top row by positive 2 and add it in there. So we're going to add 2 copies of the first row. And when we do that, we've now eliminated down here. Continuing on then, up arrow, and we're going to have the fourth row. The new fourth row is going to be the current fourth row minus 2 copies of the first row. And now we've completed the elimination steps here for our first row. Now we move down. Again, we're going to make a leading 1. So we're going to take the negative 1.5, we're going to divide the second equation, the second row, by the negative 1.5. So that's B, 2 comma colon, that's the second row, is equal to the current second row, which is B, 2 comma colon, divided by the value at 2, 2. The reason it's important to walk through a couple of these is because as you do this, you begin to see the pattern, and you begin to see, hey, if I was going to program this up, if I was going to make MATLAB do this using a for loop, which seems pretty obvious as a way to proceed, then we can kind of see how we would do that. So here we've converted to a leading 1, and now same thing. We're going to make a 0 for the 2 and a 0 for the negative 3. So I'm going to come up here, and I'm going to take the third row, replace it with the third row. I'm going to do minus 2 times the second row. So now I'm using the second row. The second row is the thing to eliminate. And when I do that, I get my 0. And now same thing, except it's the fourth row. Fourth row, and it's going to be plus 3 times the second row to get rid of the negative 3. And here we are. Now we move down to the third pivot down here, which is 1/3, and we're going to take the third row and we're going to set it equal to the current third row divided by the value that's currently in that pivot. And when we do that, we're here. And now we have a matrix that is in row echelon form. It's ready for back substitution. And in fact, if we were to write out the equations associated with this, we would see that we have a free variable here at x4, and then we have fixed variables or pivot variables for x1, x2, and x3. And we could write out the solution and we could put it in vector form just like we did at the beginning. That's how we're going to proceed. Let's take a look at the questions that we have for today. And these are the questions that you're going to do. So you're going to take this and you're going to write it in matrix vector form along with an augmented matrix. You're going to just write down, and I recommend you do it in MATLAB. Just take your augmented matrix, put it in MATLAB, and you're going to do a few steps. It's maybe 3 or 4 steps of Gaussian elimination just to get the hang of it. And then you're going to create a system down here to meet this requirement. Thanks very much, and we look forward to seeing you in class.